The Parker Solar Probe concept originates in the 1958 report by the Fields and Particles Group, a Committee A to the National Academy of Sciences Space Science Board, which proposed several space missions including a solar probe to pass inside the orbit of Mercury to study the particles and fields in the vicinity of the Sun. In 70s and 80s, NASA partnered with West Germany to send solar probe missions Helios A and B. Studies in the 1970s and 1980s reaffirmed its importance, but it was always postponed due to cost. A cost-reduced solar orbiter mission was studied in the 1990s, and a more capable solar probe mission served as one of the centerpieces of the eponymous Outer Planet Solar Probe (OPSP) program formulated by NASA in the late 1990s. In the early 2010s, plans for the Solar Probe mission were incorporated into a lower-cost Solar Probe Plus. The redesigned mission uses multiple Venus gravity assists for a more direct flight path, which can be powered by solar panels. It also has a higher perihelion, reducing the demands on the thermal protection system. In May 2017, the spacecraft was renamed the Parker Solar Probe in honor of astrophysicist Eugene Newman Parker, who coined the term solar wind. The solar probe cost NASA $1.5 billion United States dollars. The launch rocket bore a dedication in memory of APL engineer Andrew A. Dantzler, who had worked on the project. The project was announced in the fiscal 2009 budget year. The cost of the project is $1.5 billion United States dollars. Johns Hopkins University Applied Physics Laboratory designed and built the spacecraft, which was launched on the 12th of August 2018. It became the first NASA spacecraft named after a living person, honoring nonagenarian physicist Eugene Newman Parker, Professor Emeritus at the University of Chicago. A memory card containing the names of over 1.1 million people was mounted on a plaque and installed below the spacecraft's high-gain antenna on the 18th of May 2018. The card also contains photos of Parker and a copy of his 1958 scientific paper predicting important aspects of solar physics. On the 29th of October 2018, at about 18:04 Coordinated Universal Time, the spacecraft became the closest ever artificial object to the Sun. The previous record, 42.73 million kilometers or 26.55 million miles, from the Sun's surface, was set by the Helios 2 spacecraft in April 1976. As of its perihelion the 21st of November 2021, the Parker Solar Probe's closest approach is 8.5 million kilometers or 5.3 million miles. This will be surpassed after each of the two remaining flybys of Venus. The Parker Solar Probe is the first spacecraft to fly into the low solar corona. It will assess the structure and dynamics of the Sun's coronal plasma and magnetic field, the energy flow that heats the solar corona and impels the solar wind, and the mechanisms that accelerate energetic particles. The spacecraft's systems are protected from the extreme heat and radiation near the Sun by a solar shield. Incident solar radiation at perihelion is approximately 650 kilowatts per square meter, or 475 times the intensity at Earth orbit. The solar shield is hexagonal, mounted on the Sun-facing side of the spacecraft, 2.3 meters or 7 feet 7 in diameter, 11.4 centimeters or 4.5 in thick, and is made of reinforced carbon-carbon composite, which is designed to withstand temperatures outside the spacecraft of about 1,370 degrees Celsius or 2,500 degrees Fahrenheit. A white reflective alumina surface layer minimizes absorption. The spacecraft systems and scientific instruments are located in the central portion of the shield's shadow, where direct radiation from the Sun is fully blocked. If the shield were not between the spacecraft and the Sun, the probe would be damaged and become inoperative within tens of seconds. As radio communication with Earth will take about 8 minutes in each direction, the Parker Solar Probe will have to act autonomously and rapidly to protect itself. This will be done using 4 light sensors to detect the first traces of direct sunlight coming from the shield limits and engaging movements from reaction wheels to reposition the spacecraft within the shadow again. According to project scientist Nikki Fox, the team describe it as the most autonomous spacecraft that has ever flown. The primary power for the mission is a dual system of solar panels or photovoltaic arrays. A primary photovoltaic array, used for the portion of the mission outside 0.250, is retracted behind the shadow shield during the close approach to the Sun, and a much smaller secondary array powers the spacecraft through closest approach. This secondary array uses pumped fluid cooling to maintain operating temperature of the solar panels and instrumentation. On the 4th of December 2019, the first 4 research papers were published describing findings during the spacecraft's first 2 dives near the Sun. They reported the direction and strength of the Sun's magnetic field, and described the unusually frequent and short-lived changes in the direction of the Sun's magnetic field. These measurements confirm the hypothesis that Alfvén waves are the leading candidates for understanding the mechanisms that underlie the coronal heating problem. The probe observed approximately 1,000 rogue, magnetic waves in the solar atmosphere that instantly increase solar winds by as much as 300,000 miles per hour or 480,000 kilometers per hour, and in some cases completely reverse the local magnetic field. They also reported that, using the beam of electrons that stream along the magnetic field, they were able to observe that the reversals in the Sun's magnetic field are often associated with localized enhancements in the radial component of the plasma velocity. It is the velocity in the direction away from the Sun's center. The researchers found a surprisingly large azimuthal component of the plasma velocity, or the velocity perpendicular to the radial direction. This component results from the force with which the Sun's rotation slingshots plasma out of the corona when the plasma is released from the coronal magnetic field. Parker discovered evidence of a cosmic dust-free zone of 3.5 million miles or 5.6 million kilometers radius from the Sun, due to vaporization of cosmic dust particles by the Sun's radiation. That's it for today, guys. If you like this video, please subscribe to our channel. Thank you and have a great day.